In this video, we are going to make a review of the various organic reactions involving aliphatic compounds. So before we continue, I want to thank those of you who have taken time to subscribe to our channel and to like the video. For those of you who haven't subscribed to the channel, please take some time and subscribe to my channel. Like the video and share to those who will be writing the exam next year and in 2 years' time. Thank you for taking your time to subscribe to our channel. Let's get started. We will be starting with alkanes. We will be starting with alkanes and we'll go clockwise. These synthetic roots, we will be starting with alkanes and we will go clockwise. Alkanes and we will go clockwise. Starting with alkanes. You know, alkanes, they have many types of reaction. They react with halogens. They react with halogens at room temperature. They also react with halogens at room temperature. They also react, and that is by electrophilic addition. Alkenes undergo electrophilic addition by reacting with halogens. So now, one of the example of reacting with halogens is with bromine. They will react with bromine. We are starting here with bromine, the one here with bromine. Now, alkenes here from this circle here, you will see that the alkene will react with halogens at room temperature, and this is what we call that. This is by electrophilic addition on the double bond. So when they react with when alkenes react with halogens, they will give a dihalogenoalkane. A dihalogenoalkane. A dihalogenoalkane is something like a 1,2-di. For example, if we are using ethene, we are using ethene as an example, and ethene reacts with bromine molecule, which is going to be through electrophilic addition. We are going to have 1,2-dibromoethane. So it's going to give a dihalogenoalkane. So let me just write here for you to see. An example is, let me say ethene. This is ethene here. This ethene here. When ethene reacts with bromine, let me say bromine. It's a bromine molecule. You know that because of the pi electron that are here, high electron density in this region, They are going to induce a partial negative charge here, a partial positive charge. This is going to be a plus, and this is going to be a negative. And this is going to attach itself here, and it attaches itself here. The other one will attach itself here. So this is by electrophilic addition, and the product will be this is no more an alkene, it is now an alkane. So this one will attach itself here, so it will be bromine here, and there will also bromine here, hydrogen, 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 hydrogen. In that case, we say this is 1 this is 1,2 dibromo ethane. One, two dibromoethane. So here, this is the alkene. This is ethane. This is an ethane molecule. I mean, an ethane molecule. You can call this ethane. This is an ethane molecule. Then you were asked in the laboratory, you will see that bromine. The bromine is a brownish red color. This is a brownish red color, brownish red color. It's a brownish red color, and this other substance is colorless. It's colorless. Why do we say colorless? This is one of the tests for alkene. Bromine will decolorize. Bromine will decolorize bromine water. Alkene will decolorize bromine water. So now the bromine water, which is a brownish red color, will be decolorized by the alkene. Will be decolorized by the alkene because as a result of the breaking of the double bond due to the formation of what? The formation of 1,2-dibromoethane. This is colorless. That is an observation in the lab. It is an observation in the lab. So now I said this is an alkene. An example of the alkene is ethane. Ethane, when it reacts with a bromine molecule, because of the high density of electron per electron that are here, this one is that there is going to be an induction, or a partial negative charge is going to be induced here. A positive charge is going to be induced here, and the opposite side is a partial negative. Now this is a polar molecule, and then if you want the details of this, go back to our electrophilic addition reaction video and you watch the details of it. And when this reacts, what will happen? All the bromine atoms are added to the 1 and the 2nd position of the ethane, and this double bond is being broken, and only a single bond is formed. This is from ethene to ethane, and it result in what? It result in 1,2-dibromoethane. 1,2-dibromoethane. Initially, it was a brownish red color of bromine water. Now it is not. Now the ethene, because of the presence of the double bond there, would decolorize this bromine water to colorless as a result of the formation of 1,2-dibromoethane. Now let's go now to the next one from ethene. Ethene now again, you can see that again you can also see that from here ethene will react. Ethene can react again with hydrogen bromide. Ethene again can react with hydrogen bromide to produce hydrogen bromide or hydrogen chloride. Any hydrogen halide. Any hydrogen halide hydrogen bromide or hydrogen chloride, and when it reacts with that, it's going to produce what we call an alkane. An alkane is going to be produced. An alkane is going to be produced when it reacts. A halogenoalkane is going to be produced. So let's look for this other one, reaction of alkane and halogenoalkane. An example of this type of reaction here is also alkene reacting with hydrogen bromide. If an alkene reacts with hydrogen bromide, what will be the outcome? If an alkene reacts with hydrogen bromide, let me use alkene again. Alkene with hydrogen bromide. If an alkene, this is an alkene, if it reacts with hydrogen bromide, what is going to be the same? Plus a hydrogen bromide, that is a hydrogen bromide. Oh, this separate here. If an alkene is reacting with hydrogen, with a hydrogen bromide, remember the hydrogen bromide is going to be added over this double bond. It's going to be added over this double bond, and hydrogen, according to Markovnikov rule, it cannot apply here. So it must be added to the alkene. That this must be added there should be an unsymmetrical alkane. An unsymmetrical alkane is the only one. An unsymmetrical alkene like this one here, a CH3, a CH3. So now, according to Markovnikov rule, if HBr, that is a hydrogen bromide, is added to an unsymmetrical alkene. Why I call it an unsymmetrical alkene is because the hydrogen on each of the carbon are not the same. We have only one hydrogen here, we have 3 here, we have 2 here. This is an unsymmetrical alkene. So when HBr, hydrogen bromide, is added to an unsymmetrical alkene, hydrogen will attach itself to the carbon atom that has the highest or has the higher or the highest number of hydrogen. So this carbon here will attach itself here. It will attach itself here, and the bromine will attach itself but this way, and bromine will attach itself but this other way. So that is what is going to happen. So in that case, we will have, this is what we are going to have. We are going to have this. It will now be CH3 now there is a carbon here, hydrogen, there is a hydrogen there. Then I said the double bond is being broken, the hydrogen is here, there's another hydrogen is here. I said the hydrogen will attach itself to the carbon that has a higher number of, to the carbon atom having the highest number of hydrogen. There are only 2 carbons here. This one has 2 and this one has 1 hydrogen. So the hydrogen will attach itself but to this carbon atom here. So in that case, the hydrogen will be here. And in the other case, well, let me just identify it in this way so that you can better understand. You can have this one as hydrogen, and we have this as what? We will have this as bromine. Okay, we have this as bromine. So the compound that we are going to have here this compound can easily be written as CH3, CH3, CHER, and the CH3. That is how the compound can be written. So now, this compound, we can say this compound is the formation of this compound. We can call now this compound as 1, 2. We can call it as 2-bromo, 1, 2, 3. 2-bromo, 2-bromopropane. 2-bromopropane. That's why they call it. That is why that is why here it is mentioned halogeno. From here we'll call a halogenoalkane. This is a halogenoalkane that has been formed. A halogenoalkane that has been formed as a result of this. So now again, you will also see that alkane and alkane here, despite the fact that they can react with alkane can react with hydrogen bromide under room temperature, and that will be electrophilic addition to produce halogenoalkane. Alkane again can react with hydrogen. You can react alkane with hydrogen to produce alkane. Hydrogen will be acting, the nickel catalyst, or can call it platinum catalyst. Either nickel catalyst or call it platinum catalyst. All of them will be acting as catalysts. You can either use hydrogen, a nickel catalyst, or you can use platinum catalyst. And when you add hydrogen to alkene, an alkane is being produced. Let's use that one as another one. That is another reaction. That reaction is this other one here. We will have alkane. The alkane. This is the alkane molecule. Yes, that is the alkane. That is the alkene molecule. Now the alkene molecule plus hydrogen. Now it is passed through. The alkene molecule is passed through what we call a nickel catalyst. It could be nickel catalysts. Nickel catalysts. Nickel, or we can call it platinum catalysts. You will do what? You will do heating. You will heat it by heating it. Nickel catalyst, you got nickel catalyst or platinum catalyst by heating. And what you will get as a result of this is the hydrogen will be added to this position and to this other position here. This will be the resultant. An alkane will have a carbon, hydrogen, hydrogen. So now we will have a hydrogen. There's hydrogen that have been added to here. In that case, we are leaving from ethane, which is an alkane, to what we call ethane. This ethane, and that is what we call an alkane. When we call it hydrogenation. We call this process hydrogenation. Addition of hydrogen to what? To an alkene molecule. So an alkene molecule here is ethene, and on adding hydrogen using a nickel catalyst or a platinum catalyst, and by heating it, our product will be an alkane. So an alkane, and alkane is ethane. So ethene to ethane. So again, we are going to go, okay, oxidation. We are going to go to oxidation of we are going to go to oxidation of alkene. Alkenes are oxidized to different, depending the conditions. Alkene undergo oxidation, and the oxidizing agent that we are going to use here, there are two, for this product here. The oxidizing agent is acidified potassium manganate 7. Acidified potassium manganate 7. Acidified potassium manganate 7 is used to oxidize, and the acidified potassium manganate 7 that is being used is cold dilute acidified potassium manganate 7 solution. Cold dilute acidified potassium manganate 7 solution at room temperature. So the condition is room temperature. The reagent is acidified potassium manganate 7. Now, is reacting with alkene. What will be the product? The product will be a diol. By oxidizing an alkene. It will be a diol. And a diol in this case, I wanted to observe it like this. Let me clear this off. Okay. Okay, now diol. How do we oxidize an alkene? An example of an alkene. Let's take an example of the alkene to be ethane. We are still going to be using ethane. We use ethane under ethane with a cool and dilute acidified potassium manganate 7 at room temperature and pressure. Let's see the diol that is going to give. A diol is 2 hydrogen, 2 OH attached to the molecule. Let's use ethene as an example. This is an ethane molecule. That is an ethane molecule here. This is an ethane molecule. Okay, I say it is a cool dilute acidified potassium manganate 7. Okay, I have water here. When they say cool dilute, it means that there's water involved in it. Then plus potassium manganate 7. The potassium manganate 7, remember that potassium manganate 7 is an oxidizing agent. And an oxidizing agent, the role of an oxidizing agent is the provision of a water molecule. Oxygen is used for the provision of oxygen that is added. So this oxidation that is taking place, we are adding oxygen to it. This is the oxygen that we are adding. So what would be the outcome of this addition? Look at it, how I am doing it. And we are saying this is acidified manganate 7. That is acidified manganate 7, and which is cool dilute. acidified manganese 7 cool dilute, and the product that we are going to have is a diol. What will be the diol? It will be okay. We have 2 hydrogens, and we have 1 oxygen, and the other one 2 oxygen. So 2 hydrogen and 2 oxygen, all of them are going to give us 2 OH groups. So these are going to be the OH groups here. These are going to be the OH groups here. These are the OH groups. These are the OH group. Let's fill our hydrogens. So we now fill the rest with our hydrogens. Now fill the rest with the hydrogen. So our product here, this is a diol. This is a diol. This is a diol. Diol means that there are 2 OH groups on the compound. So now we can now name this as. Let's name this to be. This is ethane. That is ethane, and from ethane we can have, since ethene will now go to ethane, we'll call it ethane 1,2 diol. It is a diol, ethane. This is the carbon 1 and carbon 2. Ethane 1,2 diol. So when there are 2 OH group, we'll call it diol. When there's 1 OH group, we'll call it ol. 2 OH group diol. So ethane 1,2 diol. So that is why we say oxidation of an alkene will produce a diol. When we use cool dilute acidified manganate 7 ion, we are going to have a diol, and that is the product of it, for the example we have given. Now again, alkene. Another example, another reaction of alkene is, okay, this alkene. We are done with alkene. Okay. Let's see another reaction of alkene. We want to finish with alkene. Alkene now can undergo what we call alkene now can undergo hydration. Alkene can undergo hydration using phosphoric acid. It can undergo hydration using phosphoric acid to produce an alcohol. It can undergo hydration using phosphoric acid to as a catalyst to produce what? To produce an alcohol, and that alcohol will be ethanol. So alkene, again, alkene plus, this is an alkene, let's say CH2 plus water, and we are saying through what? Through phosphoric acid. Look at it here. It will undergo it. Yeah, through concentrated phosphoric acid. This is using as a catalyst. As a catalyst, now we will have CH3, CH2OH. We will now have an alcohol. We will have an alcohol. We will have an alcohol in this case. We will have alcohol in this case. So now again, with alkene again, alkene undergo a type of reaction again at high pressure catalyst. There is polymerization. it should be remembered that alkene undergo what we call addition polymerization. Alkene undergo what we call addition polymerization. And with this addition polymerization, addition polymerization, alkene can form many other polymers. For instance, let me use an example here. Alkene, an alkene can undergo an alkene, for instance, ethene. Ethene, for instance, this, let me say, this one. This one, or let me put it this way. Okay, we can have this, let me say this is the alkene. This is the alkene. Yeah. We have n numbers. We don't know the number of alkenes that are here. Let's say alkenes, the number of alkenes that are here is n number of alkenes. When this n number of alkenes under the condition, the high temperature with the catalyst, they can polymerize by adding each monomer on the other one. It's a repeated addition of many of the monomers to form what we call the polymer. And so this can now result in a polymer like this one. Can result in a polymer like this. This polymer can be, that's a hydrogen. This is a polymer. This is a polymer. A polymer, depending on the number of alkene that were formed, that were added. So we can even call this is an ethene molecule. And this is an ethene molecule, and we can call it, which is a monomer. And this one is a polymer. We call it polyethene. Polyethene, which is a polymer. The same thing can go with. It can happen with. Let me say propene, for instance. Propene. Let's take propene for instance. Let's use propene for instance. Here is propene. Propene is written like this. It could be like this. We have and we have it like this. Propene like that. This is propene. Propene, if it polymerizes, we are going to have something like this. We are going to have something like this so this could be N. So n number of propene added together. Since it is an addition reaction, we are going to have this one, and we can call this one polypropene. Yeah, polypropene. And call that one polypropene, which is still a polymer. And that is why we are saying here that alkene at high pressure it will undergo what we call polymerization. And the type of polymerization alkene will undergo, we call it addition polymerization. So now, let's go to the next compound for conversion. Okay. Now we are done with alkene. The halogenation, electrophilic addition, oxidation of alkene, reaction of hydrogenation of alkene by adding hydrogen. We are done with alkene, addition of a hydrogen bromide to an unsymmetrical alkene, and applying the Markovnikov rule, and hydration of alkene to form alcohol using concentrated phosphoric acid. Now let's get now to there is one other thing on alkene, on the oxidation. There are two conditions of oxidation of alkene. The first condition of oxidation of alkene is cool, dilute, acidified potassium manganate 7 at room temperature. But you can still use hot concentrated acidified potassium manganate, and this would be the product of using hot concentrated acidified potassium manganate 7 a solution. If you use hot concentrated, let me say we want to use an alkene to be this one. I want to give an example of this alkene to be this. If you use this type of alkene here, that's another condition. In that condition, it will not be a diol, but it will be another compound. Take, for instance, oxidation of this type of alkene. This alkene here, which is this one. We have this alkene with the alkene that has two alkyl groups attached to their ends, to both ends. Now, two alkyl groups attached to both ends. What is going to happen here is this one. We are not going to do oxidation. This is oxidation. It should be recalled that this is used as oxidation. This symbol is used as oxidation. A square bracket is used as oxidation. So if we use this square symbol, we are saying that two oxygen have been donated to this compound, addition of oxygen to this compound, and two oxygen atoms. So this is what we are going to have when we are using this condition, using hot concentrated acidified potassium manganate 7 solution. What happened is that there is going to be a breakage. There's going to be a breakage in the middle here. There's going to be a breakage of the double bond. The condition is hard. It is hot concentrated acidified manganate 7. So now, because of the harsh condition, it's going to break the double bond instead. The double bond is going to break. There's going to be a breakage in the double bond. And when the double bond breaks, what happens? Oxygen will add to the two double bond. So see what happens here. See what happens here. If you need more details, just go back to our previous video on oxidation of alkene. You have more there. This is what will happen. These are the products that you are going to see. These are the products that you are going to see there. CH3. It breaks the double bond into two equal parts, and this is what you are going to have. Plus this other double, this one. And this is what you are going to get. You're going to get this one and this one. In that case, we now have two ketones. These are two ketones. We call them. This is propanone. Yeah, this is a propanone. 1, 2, 3. This is a propanone. Two ketones are being formed. Two ketones are being formed as a result of this breakage. Another one. This is one. This is 1. 2. Another one. Should in case we have an alkene. Excuse me. Should in case we have an alkane that has an alkyl group like a methyl group, an alkyl group, and a hydrogen on one side, this is what is going to happen. We have this carbon. We have a methyl group here. This is a methyl group. This is another methyl group. This is a methyl group here. And this is a hydrogen. And they're using this very condition. The condition is hot concentrated acidified manganate 7 ion solution. This condition is hard, and since it is a harsh condition, it's going to do what? It's going to lead to the breakage of this, and it's going to lead to the breakage of this, and it's going to break equally. It's going to break equally. And when it breaks equally, what is going to happen? Okay, I said it is addition of oxygen. So we now have oxygen added. So when this one breaks, when this breaks, it breaks equally. This is going to be the product. We are going to have C, methyl group, a hydrogen, and this one. And this one plus plus this one, a methyl group, this N, and this other N. Oxygen will also be attached here. So now these are the two products from this oxygen. These are the two products. But it should be remembered that this is a ketone, but this one is an aldehyde. This is a ketone, and this is an aldehyde. So this aldehyde is ethanol. This aldehyde here is ethanol. Remember that aldehydes are oxidized. So it is still in the oxidation chamber. It is an oxidation chamber, and it is an aldehyde. Aldehydes are further oxidized to what? To carboxylic acid. So this will be the product. This will be the product that we are going to have here. This will be the product that we are going to have. We will have CH. We will have a CH3. We will have a CH3. This is the product that I've written here. That is the CH3 here. This is the carbon and the double bond. Now it is further oxidized. It is further oxidized again to what? Using our agent. It is still in the oxidation chamber. That is why the oxidation is going to occur. We will have this. And what will be the product? Our product will be what? it will be a carboxylic acid. It will be CH3. That will be an ethanoic acid that's going to be formed. Then another condition, if the carboxylic acid is, if the alkene, number 3, if the alkene has only hydrogen at one end, let me say this is the alkene, oxidation of the alkene. Let me say this is the alkene. The alkene is, let me say this one, it has hydrogen at both ends, hydrogen. And we have this one, it has this one. Okay, now I said that under this harsh condition, what happens? Under this harsh condition is going to break equally. It's going to break equally. Now there's addition of oxygen. But it should be noted that if it wants it when there are only two hydrogens, we are the two hydrogens. When there are only hydrogens on one end of the carbon, when there are only once more, when there are only hydrogen on one end of the alkene, that end is converted to what? To carbon dioxide and water. On one end of the alkene, where we have only carbon and hydrogen, that end is converted to carbon dioxide and water. Then, for instance, this one here, when the bond breaks here, we have, let me say, four oxygen here. Now it will be carbon dioxide. This end, the carbon will be converted to carbon dioxide. The hydrogen will be converted to water. Then this other end here, since there are two alkyl groups here, we will have our ketone plus our ketone, which is there, which will be carbon so that will be the product. So the condition here is that when one end has only hydrogen and a carbon there, that end is converted to what? To convert it to carbon dioxide and water. Where there are alkyl groups, where there is an aldehyde group, it is converted to carbon dioxide to carboxylic acids. So this is the condition under which, the condition here is oxidation of alkene using hot concentrated acidified manganate 7 ion solution. Unlike the other one is cold dilute acidified manganate 7 ion solution. That one gives diol. That one, the condition is not harsh, it gives but diol. But the condition here is harsh. It leads to the breaking of the double bond. Now let's go back to alcohols. We'll go to alcohols. Let's go to alcohols now. Let's go to alcohols. You see the reaction of alcohols here. Alcohol, the first thing with alcohol is that alcohol will undergo the reaction here. The alcohol will undergo oxidation. The the alcohol will undergo oxidation. And when they undergo oxidation, let me say for oxidation. Now, alcohol will undergo oxidation. Alcohol will undergo oxidation. Now, alcohol are oxidized. Alcohol are oxidized to alcohol are oxidized to it depends the type of alcohol. It depends the type of alcohol. For instance, here we have the alcohol. The generally alcohol. Now, alcohol are oxidized using acidified potassium dichromate. Acidified potassium dichromate 6. This is acidified potassium dichromate 6. This is an oxidizing agent, and alcohol can be oxidized. Now, if primary, what happens is that it is oxidized to aldehyde. Okay, let me give an example. Let me give an example using examples here. Okay. Excuse me. Let me clear the board. Okay. Back. Okay. I said alcohol can be oxidized. Alcohol can be oxidized to to aldehydes. Here, alcohols from the flow chart here. The flow chart here describe alcohol are oxidized to aldehyde. If it is a primary alcohol are oxidized to aldehyde. Meanwhile, secondary alcohol are oxidized to what? To ketone. And the oxidizing agent used is acidified potassium dichromate 6. Okay, let me just give you an example here. An example here for the reaction. Let me say an example of the alcohol is, let me say primary alcohol is, let me say CH. For primary alcohol, I can have, for primary alcohol, we can have, let me say, ethanol, yeah, CH3, CH3, yes, primary alcohol, that is, or but this thing. Okay, we will have here, we will have ethanol as a primary alcohol. Let me say CH3, CH3, hydrogen, that is ethanol. Now ethanol is undergoing we said the oxidizing agent is acidified to O7 2 minus, yeah, this is acidified potassium dichromate, and now it is acidified potassium dichromate. We need oxidation, and this is a symbol for oxidation. That is a symbol for oxidation. Now, what will be the product? Now, this will be our product. Our product will be this one. That will be our product, and our product will be ethanol. Our product will be CH3. Will be CH3. And a hydrogen plus a molecule of water. Plus a molecule of water. This ethanol. That is ethanol. That is the oxidation of a primary alcohol. This is ethanol. Call it a primary alcohol. That is the oxidation. Now using a secondary alcohol, for instance propan-2-ol, we will have something like this. If I say I want to use by the secondary alcohol, let me say CH3, carbon, OH, it is propan-2-ol. This is a secondary alcohol. It undergoes plus, okay, plus, I said addition of oxygen. Addition of oxygen is going to give us this. Under this condition, we are going to, under the condition of oxidation is, they say it is acidified potassium, potassium dichromate 6. Under this condition, we are going to have primary secondary alcohol oxidized to ketone. Secondary alcohol are oxidized to ketone. Secondary alcohol are oxidized to ketone plus water. Water that is there. Secondary alcohol are oxidized to ketone plus water. Plus water. Okay, this is what is happening here. See what happens here in the as a result of this oxidation. See what is happening here. A molecule of water must be removed. So what do we do to remove this molecule of water? We will do like this. We will do like this. A molecule of water has been removed. A molecule of water has been removed. This is the molecule of water that has been removed from here to give us this ketone. So we have this propanone, propanone, which is a ketone. Secondary alcohol oxidized to ketone, and this is what we call propan-2-ol. Propan-2-ol. That is a secondary alcohol. This is a secondary alcohol. That is what is being done. So secondary alcohol can be oxidized. So secondary alcohol. So a recap, we say that secondary alcohol can be primary alcohol can be oxidized using acidified potassium dichromate to corresponding ethanol. To ethanol, but it should be remembered. That since it is ethanol, if ethanol is not removed as soon as it is being formed, this is further oxidized. This is further oxidized to what we call carboxylic acid. This is further oxidized to what we call. This is further oxidized to. It is further oxidized. It is further oxidized to what we call ethanoic acid. CH3 COH. So this is further oxidized to that one if this one is not removed. So now primary alcohol, secondary alcohol on the other hand, using acidified potassium dichromate 6 is oxidized to a ketone, and this is how I've shown you how the whole thing. I gave an example as propan-2-ol. That's being oxidized to propanone and water. So now that is oxidation of alcohol to ketone and to aldehyde. So now we will proceed now. It should also be remembered that these aldehydes are further oxidized, as I told you. The aldehyde are further oxidized to carboxylic acid. So that is the whole thing. The aldehydes are further oxidized to carboxylic acid. As I showed you here, aldehydes are further oxidized to carboxylic acid. That is ethanol to ethanoic acid. Now again, I go now to aldehydes again can undergo reduction again back to what? Aldehyde can undergo reduction again back to primary alcohol. They can undergo reduction using lithium tetrahydroaluminate. They can undergo reduction to using lithium tetrahydroaluminate to that one. So let me just show you how aldehydes can undergo, and aldehydes here can undergo reduction using lithium tetrahydroaluminate to back to alcohol again. Then ketone again can undergo reduction again back to alcohols, back to a secondary alcohol. So now let me show you again how you can come about this. Let me show you how you can come about this one. Sorry. Okay, please give me some time. Sorry, please. I said aldehydes can be oxidized. Reduced. Aldehyde can undergo reduction. Reduction of aldehydes to primary alcohol. For instance, we can oxidize. Let me use an example of propanal. Propanal is CH3. Propanal is CH3, CH2, and CHO. CHO. Now, these can undergo what we call oxidation. A reduction. It can undergo what we call reduction to primary alcohol. For instance, reduction is using lithium tetrahydroaluminate. You can either use lithium tetrahydroaluminate, or you can use sodium tetrahydroborate. You can either use lithium tetrahydroaluminate, or you can use sodium tetrahydroborate. So now we are oxidizing this one, we are reducing this one back again. We can, by reduction to what we call primary alcohol. The primary alcohol for propanal is propan-1-ol. So propan-1-ol will be this one, CH3, CH2, CH2, OH. That will be the whole thing. So what we need here is that how many hydrogen have been added? The hydrogen have been added. We'll have to add 2 hydrogens here. We have to add 2 hydrogens here, and 1 other hydrogen. So we will have there are 2 hydrogens that are needed for this. So in that case, we will have 2 here. We'll put a 2 here. Okay, we'll put a 2 there. So we are using lithium tetrahydroaluminate. You can write here that lithium tetrahydroaluminate, LiAlH4. We use that by the lithium tetrahydroaluminate is a reducing agent. It's a reducing agent, and the purpose of the reducing agent is to provide the hydrogen. Unlike in oxidation, the purpose of oxidizing agent is to provide oxygen. So now this is for primary alcohol. Then ketone, reduction of ketone. Let's see how ketone can be reduced to secondary alcohol. For example, the ketone, this is a ketone, CH3. This is CH3CO, CO, and then CH3. This is a ketone. A ketone can be reduced now using the same condition to what we call secondary alcohol as CH3. CH3. So we are going to add oxygen. We are going to hydrogen is required. The hydrogen that are required will be this one. How many hydrogen are required? The hydrogen required primary alcohol will be this. Will be here. That will be CH. This is hydrogen here. There's OH here. Yeah, then CH3. You see that this is a secondary. This is a secondary alcohol. So how many hydrogens are required? The hydrogen required are just this one and this one. So there are 2 hydrogen that are required here. So 2 hydrogen are required to produce. So we can use, we can reduce a ketone to secondary alcohol. So we can still use lithium tetrahydroaluminate. Now again, carboxylic acid again. We can still reduce carboxylic acid. Carboxylic acid again can be reduced. For example, ethanoic acid that we got the other time, can be reduced again back to the primary alcohol. And this is how we can do it. This is ethanoic acid. This is ethanoic acid. Ethanoic acid is this one. Ethanoic acid, COOH plus to give ethanol. It will be CH3, CH2, CH2OH plus water, because there are two oxygen here. So now we will need hydrogen there. The hydrogen here, we need hydrogen. We will need hydrogen here. Okay, how many hydrogen are needed? We have added hydrogen here, 2 hydrogens here. We need to add 2 hydrogens here. Then we need to add other 2 hydrogen to make a molecule of water. So hydrogens to be added here are altogether 4. There are 4 hydrogen that are being taken away. And using the same condition, it is lithium tetrahydroaluminate. So we can do this. We can reduce aldehydes to primary alcohol. We can reduce ketone to secondary alcohol, and we can reduce ethanol. We can reduce acids, carboxylic acids, back to corresponding primary alcohols. So now let's go back to here. Okay, now back we are done with alcohols, we are done with ketones, Now ketones, it should also be remembered that aldehydes can react. I mean, alcohols, we are not done with alcohols. Alcohols can react with acids. Alcohol can react with carboxylic acids. They can react with carboxylic acids to form esters. Alcohol can react with carboxylic acid to form esters. Then carboxylic acid again can react with alcohol to form esters. And we use concentrated sulfuric acid as a catalyst. The alcohol plus the carboxylic acid is heated with concentrated sulfuric acid, which is used as a catalyst, and the resultant or the product will be an ester, and this process is called esterification. Now, again, aldehydes can react with hydrogen cyanide. Aldehyde can also react with hydrogen cyanide, and ketones can also, aldehyde can react with hydrogen cyanide to form hydroxyl nitrile. Ketone can also react with hydrogen cyanide to form hydroxyl nitrile. An example of aldehyde that can react with hydrogen cyanide to form hydroxyl nitrile, and this type of reaction with aldehyde and hydrogen cyanide, we'll call it addition, a nucleophilic addition. Here, the nucleophile here will be the cyanide. Remember that potassium cyanide is very toxic. Potassium cyanide is very, very toxic. So potassium cyanide is reacted with sulfuric acid to bring down the toxicity. It is reacted with sulfuric acid to produce what we call hydrogen cyanide. It is the hydrogen cyanide that dissociates in solution to produce a cyanide ion. It is now the cyanide ion that is going to be acting as a nucleophile. It's a cyanide ion that is going to be a nucleophile that is going to be added onto the aldehyde or onto the ketone, and the resultant will be a hydroxyl nitrile. And this is, let's use an example here. Let me give you an example there for you to understand. Okay, aldehyde plus aldehyde reacting with potassium cyanide. In this case, hydrogen cyanide. Now, this is the reaction with aldehyde. I want to take an example of an aldehyde, which is an example of the aldehyde reacting here is an example of the aldehyde reacting here is let me say ethanol. Ethanol would ethanol produce hydroxynitrile? Okay, let's see. If you want the details of the mechanism, that's why I'm just going to the equation. If you want the details of the mechanism, please visit our previous videos on nucleophilic addition reaction. Nucleophilic addition reaction of ethanol, nucleophilic addition reaction of ketones. You will see them there. But I am going straight back to the equations. So now, see what happened when an aldehyde, for example, here is ethanol. This is an example of ethanol, CH3, ethanol is this one. If it reacts with hydrogen cyanide, I told you hydrogen cyanide is produced as a result of the reaction of potassium cyanide plus sulfuric acid. So the hydrogen cyanide is being produced, and when the hydrogen cyanide is in solution, it will dissociate to form the hydrogen ion and the cyanide ion. It is the cyanide ion that is going to act as a nucleophile. So now hydrogen cyanide, the hydrogen cyanide will be added here. This is the product CH3. This is the OH hydroxynitrile. So when an aldehyde reacts with hydrogen cyanide, it's not the potassium cyanide. They all will react to produce this, and this one will break down to produce hydrogen. The cyanide. The cyanide ion now adds here. The cyanide ion now adds. So what happened here is this is the ethanol. This is ethanol, and this is 2-hydroxyl propanitrile. 2-hydroxy propane nitrile. There is very important. There's something which is very important in this type of reaction. What is very important in this type of reaction is that it leads to the addition, reacting with hydrogen cyanide. Reaction with hydrogen cyanide leads to the addition of an extra carbon atom. The carbon chain increases as a result of this type of reaction. They can ask you, why is this type of reaction very important? So the importance of this type of reaction is that it leads to an increase in the number of carbon atoms, or the carbon chain increases, because initially it was ethanol, but now we are going to what? Propane. 1, 2, 3. There are 3 carbon atoms that are there. So it is 2-hydroxy propanitrile. If we were to react propanone, for example, as a ketone with this, propanone will be in this way. Propanone is this is C. Yes, CH3. CH3 plus hydrogen cyanide. Hydrogen cyanide. What we are going to have here will be a CH3, a C. There will be a OH2 the same position. There will be a cyanide the same position, but instead of hydrogen here, there will be a methyl group. There will be a methyl group. So it also leads to the addition of another carbon atom there. So we can say that this is a propanone. Propanone. This is propanone. This is 2-hydroxyl. This is 2-hydro. This is 2-hydroxyl. 2-hydroxyl 2-methyl. 2-hydroxyl 2-methyl propane nitrile. Propane nitrile. 2-hydroxyl 2-methyl propane nitrile. This is another. This is the type of reaction that occurs, leading to what we said. The reaction here, which we said the reaction here, ketone will react with additional reaction, nucleophilic addition to form hydroxyl nitrile. They did not give you the hydroxyl nitrile because they did not give you the ketone. So I've given an example of ketone, and this is the product. I've given an example of aldehyde, and this is the hydroxyl nitrile. So these are the reactions here. So now we will be going to amine. The amine groups here are, we can react a halogenoalkane. We can react a halogenoalkane. We are going back to halogenoalkane. Let me go first to alkane. Let me go back again to alkane and come down to halogenoalkane. Alkane will undergo two types of reaction, and the first type of reaction that alkane will undergo is halogenation, and this is by substitution. It is by normal substitution. It will undergo by normal substitution. The second type of substitution that alkanes are going to undergo will be a free radical substitution. So for a normal alkane to undergo this type of reaction, this will be a type of, let me just give you a clue of what will happen. Let me just give you a clue of what will happen when an alkane will undergo a substitution reaction. For instance, this one. Let me just show you some examples of alkane. The normal substitution, and the free radical substitution of alkane. So now, okay, the first substitution of alkane, because here we have alkane can react with this to form halogenoalkane. Okay, now they will also react and a free radical substitution. There are two types of substitution that alkane: halogenation of alkane and free radical substitution. Now, the first one is length of alkane. I want to take an example of the alkane. The example we are going to be dealing with. Let me use methane. Methane. Let me use methane. Methane as an example that we are going to deal with is CH4. Methane is a CH4 plus chlorine. This is a chlorine. Will undergo under UV light. Under UV light, there will be on substitution. The alkane molecule, the chlorine molecule will break into two and substitute one of the hydrogen here, and then one of the hydrogen will leave, and hydrogen bromide will be formed. So we will have a CH3 plus hydrogen chloride. Let me do it so that you better understand what I'm saying. This is a hydrogen. This is this. this is this, and this is this, plus a chlorine and a chlorine, and over UV light, light, what will happen is that you will have, there is a breakage here, there is a breakage here, there is a breakage here, and there is also a breakage here. There is a breakage here, the two breakage. So what happens here is, now one of the hydrogen will attach itself here, and this will come and attach itself here. So we are going to have this as this molecule. They will be like this: hydrogen, 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 and the chlorine, plus it will be hydrogen and the chlorine. So that is how we do it, and we call these chloromethane. We'll call this chloromethane. This is chloromethane. 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 And this is hydrogen chloride. So now we can use that chloromethane again and undergo another substitution. The chloromethane can undergo another substitution, that is CH3, CH3, Cl. Then we react with another chlorine molecule plus chlorine molecule. Now, still under the UV light, it will break, and the one hydrogen will break. It's going to be substituting all the hydrogens here. So one hydrogen, when it breaks off, is going to substitute one of the hydrogen here. So when it breaks off, it will be CH2. Now when it substitutes one hydrogen here, now there will be two chlorine there. It will be Cl2. It will be Cl2 plus one of the hydrogen plus one of the chlorine will give hydrogen chloride. Now again, this will have to go down again, and there will be another substitution. It will be CH2, Cl2 plus chlorine. And what happens? There's a breakage here. It's also one of the chlorine here. So it will be only CH. The number of chlorine have increased, which will be Cl3 plus hydrogen chloride. Hydrogen chloride. Now, this one will now finally react again. It will be CH3. Will be Cl3 plus hydrogen plus chlorine to give what? Now, one of the last chlorine hydrogen is substituted. We will have Cl4 plus a hydrogen chloride. The first one is chloromethane. This one is dichloromethane. This is dichloro. It is dichloromethane. This is trichloromethane. And this is what? This is trichloromethane, trichloromethane, and tetrachloromethane. Tetrachloromethane. That is how the normal halogenation of normal substitution of chlorine will take place. But on the other hand, there is what we call a free radical substitution. What is a free radical? A free radical is an atom with an unpaired electron. Electrons are usually two. They are always two in the orbital spinning in opposite direction. But in this time around, when you have an atom with only one electron, an unpaired electron, we call that a free radical, and it's very, very reactive. Let me show how a free radical will operate. There are three stages in the free radical substitution. We have the initiation stage, we will have the propagation stage, and we will also have, now this is the normal one, then the free radical stage for alkane to halogenoalkane. Now the free radical stage is this one. We will have the first stage is the initiation, where there is initiation stage, which is the first stage of the free radical. Okay, now the first stage is initiation first. The first stage, what we call the initiation. Under the initiation stage, what happened there is that the chlorine, or the halogen, will split into two, sharing the bonding electron. For instance, this is chlorine. This is a chlorine. This is a chlorine molecule, and in this chlorine molecule, remember that this chlorine molecule, for this bond to be like this, there is a pair of electrons that they are sharing. They are sharing a pair of electrons. There is a pair of electrons here that is being shared. There's a pair of electrons that is being shared. Then, for this to happen, something must happen there. So, in that case, there is going to be what we call, at this initiation stage, there's going to be the splitting. There's going to be the splitting, and one electron will go to and this other electron will go to this other one. And they are half arrows. There's something you should notice. They are half arrows. Half arrows mean that it's only one electron that is moving. Half arrow means that there's only one electron. So one electron will go. The two pair of electrons are going to be unpaired. One will go to one side, to one of the atoms, and the other one will go. And this is the condition. Under the UV light, they will generate what we call a free radical. This is the free radical. It's UV light. A UV light, and we call this type of fission, this type of breakage, the fission, we call it homolytic fission. Homolytic. We call it homolytic fission, and this is what will happen there. This one will come here, and this one will come here, and this is a free radical. It's a free radical and a free radical. That's how you do it. Now the second stage of this, will be propagation. Propagation. In the propagation stage, there is a free radical reacting with the molecule. So for instance, here I take methane. This is methane. This is a methane molecule. This is a methane molecule. This is CH3H. This is a methane molecule plus free radical. With a free radical. This is a free radical. So what happened here is that the methane molecule, what happens there is that the molecule will break. The molecule will break. Here, it will break, releasing what? This will go, all what is happening here will be homolytic fission. It will break, releasing see here, at this stage, we are going to be producing but free radical. See here, this is, of course, there is a pair of electrons here. So what happened is that when this happens, you will see the bonding electron will split, and when it split, what happened? A free radical is going to be formed. Now, one of these free radicals here will join with this one to form hydrogen chloride. Will form hydrogen chloride. Then the CH3 will remain as a free radical with its own electron, CH3, with its own one electron. So they will be splitting here. One of these will react with, so if one free radical will react with this other one here with one electron, and a hydrogen chloride will be formed, then the free radical here will be formed. Now, at the termination stage, the last one is termination stage. The third one is termination stage, is termination. At the termination stage, a free radical is reacting with a free radical. For instance, this is a free radical plus another free radical. The product is a chlorine molecule. Then, this is another free radical plus another free radical. The product is ethane. So at the termination state, a free radical is producing, a free radical reacts with another free radical, and the reaction completes. Then at the propagation stage, there must be a production of a free radical. Then one of the free radical will react with the other one, and hydrogen chloride is being formed. So these are the stages that we will undergo at this level. Now, amines, then finally, amines will undergo can react with acyl chloride at room temperature. It will be nucleophilic addition, and we'll have a secondary amine. Then amine 2 can undergo a haloalkane nucleophilic substitution, and we'll have secondary amine, and we'll also have tertiary amine. Halogenoalkane can undergo ethanolic. Halogenoalkane can undergo ethanolic. We call it ethanolic ammonia. Ethanolic ammonia, or ammonia in alcohol. Ammonia in alcohol, or alcoholic ammonia, or you can use it. You can still call it ethanolic ammonia when ethanolic ammonia is heated with bromoethane, for instance. Is heated with a bromoethane. Bromine is substituted by an amine group. This amine group to form an ethyl ammonium bromide salt, and this reaction will continue until an ethyl amine, which is a primary amine, is formed. That is how the reaction goes. So that is the last stage of it. So thank you for listening. All these synthetic routes, you can go over them, do your revision through them, and prepare for your exams. These are all aliphatic. They are all aliphatic synthetic routes. I call them aliphatic synthetic routes because aliphatic compounds are compounds with straight chain, branch chain, or cyclic organic compounds, but not including benzene. So for those of you who haven't subscribed to our channel, I am advising you, please try and subscribe to our channel. Like our videos, and share the video with fellow learners, especially those who will be sitting for the exam next year or in 2 years' time. Thank you very much.